So properties of a semiconductor. Let us begin with what are the properties rather than discussing what it is actually is. So resistivity as one of the main property that will help us to understand more about semiconductors. Resistivity values are from, not the actual values, it's between conductors and between the conductors and insulators. If you want some specific number, I can tell you about 0.5 ohm meter, around something this. Okay, this is the resistivity of a semiconductor value. As said, it is between conductor and insulator. Actually, a semiconductor is at a very low temperature, it is a insulator. At a very high temperature, it is a conductor. That we will discuss the temperature dependence, and it has a negative temperature coefficient. For example, if you take a metal, as you increase the temperature, you have rho, which is resistivity equal to rho naught into e power alpha t. It increases with respect to temperature in exponential. Resistivity increases. That log graph will give you a straight line where alpha is the nothing but the coefficient, temperature coefficient of resistivity. Okay, but for a semiconductor, when you increase the temperature, more amount of electrons will start leaving the covalent bonds. We will discuss covalent bonds and start uh, forming a layer above the valence band and will start conducting. So for a semiconductor, temperature, as when temperature increases, the conductivity is increased. So that is why negative temperature coefficient of resistivity. Okay, now here the same semiconductor material, the enhance the conductivity with the help of another doping material, another impurity, usually metallic or non-metallic impurity also can be used. That is, adding impurity is nothing but doping. Okay, in this picture on the left side, what you are seeing is a germanium atoms which are covalently bonded. That means every germanium atoms, we know for germanium atom there are 4 electrons in the valence shell. Now these 4 electrons require another 4 electrons from the neighboring germanium atoms, so that its outermost shell is being stable. That means it requires 8 electrons. That means 4 plus 4 is required, so 4 of them will be contributed by the neighboring atoms. So all these electrons are covalently bonded to each other. All these 8 electrons are covalently bonded, and these electrons do not take part in conduction. Okay, so how is covalent bond formed? Covalent bond is formed by sharing of electrons. So these electrons, which is shared, do not take part in conduction because they are not free. Not free means they are being given some duty. Okay, so they are not free. Here we have a germanium crystal. This is a crystal as a whole, germanium crystal as well as silicon crystal. It's a group of atoms. Now it starts from, there is a first band which is comparatively very smaller because it has got only small few number of atoms, 2 electrons. Okay,
So first band, second band, third band, and the fourth one, first will contain 2, then 8. This is 8, and here you have 4 electrons. This valence band consisting of 4 electrons means this band is constituted by the energy of 4 electrons. Now, to make this valence electron conducting, it should jump to conduction band. That means each electron here should attain an energy of 0.7 electron volt. That means if by some means I am able to give this electron 0.7 energy, it will jump to conduction band and it will conduct. Okay, please don't confuse it with our barrier voltage. Barrier voltage is a different voltage, and this is for pure crystal. Pure, when we are talking about the energy gap in this PN junction diode, you have PN junction, silicon diode and germanium diode. You say about germanium diode is about 0.3 volt and silicon about 0.7 volt. This is a barrier voltage developed when you are constructing or when you are building a germanium or silicon impure diode, impure or extrinsic semiconductor. Okay, now similarly on the right you have silicon crystal, where first, second band, third band will have 4 electrons. For this particular electrons here, it requires 0.11 electron volt of energy to go to conduction band. Okay, until and unless it is reaching the conduction band, it do not conduct. Electrons do not conduct in valence band. Only when it comes to the conduction band it can conduct. Now for that particular reason, we will add some impurities to it, to the given crystals, so that it starts conducting. An extra electron or an extra hole is created such that the gap is overlapped. This conduction band and valence band get overlapped. This energy gap get reduced between the valence and conduction band. Energy get reduced and the electrons can easily go to conduction band and result in conduction.
Now this is temperature dependence on, actually this is on conductivity. Yeah, resistivity or conductivity, both are same. Now what happens when temperature increases? For a pure crystal, pure semiconductor crystal at low temperature, it will be in the valence band. The 4 electron that we are talking about will be in the valence band. 4 or 8 electrons, it will be in the valence band. And as soon as you start increasing the temperature, it will leave out the bonding will start breaking and it will reach the conduction band. And what does it mean? At a point, at a certain temperature, you can convert a non-conductor, that means an insulator, to a conducting material just by increasing the temperature. So this is what you mean by semiconductor, why it is called a semiconductor. Now coming to the type of semiconductor. Intrinsic semiconductor means it is an extremely pure form of any material. If we are talking about silicon, it is a pure silicon. If you are talking about germanium, it's a pure germanium. And can you tell me why carbon is not a semiconductor even though it has 4 electrons in the valence shell? It has got 4 electrons in the valence shell, but why carbon is not a semiconductor? We start talking about silicon, germanium. We don't talk about carbon. Just think about it. Now, that is about extrinsic semiconductor. Sorry, intrinsic semiconductor. Coming to extrinsic semiconductor. Extrinsic means whenever we add some impurity, it becomes extrinsic semiconductor. Whenever we add some impurity, it becomes extrinsic. As earlier said, we can add metallic impurity as well as non-metallic. Group 5 you can add, sorry, group 3, group 5 also you can do. Group 5 elements for acting as impurity. If you make it group 5, it is a n-type semiconductor. We will discuss in detail what is it is. And if you add a group 3 material, it will be a p-type semiconductor. Now, n-type semiconductor. N-type semiconductor, when you are adding a pentavalent impurity. Pentavalent means in the valence electron there are valence shell there are 5 electrons. If there are 4 electrons, each electron will be covalently bonded. And if there are 5, one electron will be missing. Where do that one electron stay? Electron stays in the interstitial gaps, somewhere between the atoms, and that atom cannot lie in the valence shell or inside the valence shell, because inside the valence shell it is already filled. It has to go out of the valence shell, but it is well within the vicinity of the atom. Vicinity of the atom means the nucleus is still having a hold on that particular atom, sorry, that particular electron. It is not completely away, but it is that much far from the nucleus such that, or so that, it can take part in the conduction. So this is how what is being done. On the valence band you have these electrons which are covalently bonded, but due to impurity, that one extra electron will go to the conduction band. This is about n-type semiconductor.
Here are few notes. Now, what are the notes? A new free electrons are many new free electrons. That means, as if you have a crystal, silicon, let us call it a silicon crystal pure. Now, when I add an impurity, that means pentavalent impurity, this will be in 1 in 1 million. That means out of 10 to the power 6 atoms of silicon, there will be only one pentavalent atom. Even this addition, this much small addition of pentavalent atom will produce large number of free electrons in a crystal, so that it will take part in conduction, so that the free electrons that is produced will take part in conduction. So that is why these pentavalent impurities are used. It is used in very small amount for a PN junction. Now, at a room temperature, the second point is, even at room temperature, this electrons get excited from the given position, and it forms electron hole pair. Electron hole pair will be formed, and these electron and holes also take part in conduction. Because at room temperature they will gain the thermal energy, and if they cross the conduction, come to the conduction band, it can also take part in conduction of electricity. Okay, and So there is a conduction takes occurs due to electrons as well as holes. Okay, but the number of holes will be very small in number, and it depends on the temperature. Number of holes taking part in a conductivity in a n-type semiconductor will be very small. Okay, it will the dominance is for electrons over the holes. That means holes are in minority, so these are called minority charge carriers. Minority charge carriers. And the electrons in n-type semiconductor, it is majority charge carriers. That means your actual current will be contributed by electrons rather than holes. Now we have seen for n-type conductivity. In n-type semiconductor, the conductivity is due to n-type, that means negatively charged particle. What is a negatively charged particle here? That is electrons. So those electrons are the one which is responsible for conductivity. So negatively charges, and it is called n-type electron or electron type conductivity. This is for n-type semiconductor.
Now, p-type semiconductor. P-type semiconductor means the trivalent impurity. Instead of 3 electrons being shared, sorry, instead of 4 electrons being shared, now here we have only 3 electron. Now, once we have only 3 electron to satisfy the covalently bonded. So, as stated, it needs 8 electron to complete an octet. Okay, now what we will do, this there is an absence, this absence of this particular electron becomes a hole. A hole means a attraction of electron, a strong center of electron affinity. All right, now this holes, once the neighboring atom gives the its electron to its, it will keep moving. That means the holes will start forming, holes will start moving. That means conduction is by positive holes, positive holes, that is p, positive. That is why it is called p type semiconductor. Now look at this, even in the conduction band these are electrons, and in the valence band what you have, in the valence band you have holes. Even though the conduction is done by the electron, it's actually coming and occupying these spaces from the conduction band, making these holes. So indirectly we can say that holes are the responsible, one who is responsible for the conduction of in a p-type semiconductor. Now let us see what are the majority and minority carriers. For an n-type semiconductor, we have seen it is being doped with a pentavalent atom. Pentavalent atom, 5 electrons. So one electron is extra. That means majority carriers is electron. Majority carriers is electron. Now there are minority carriers as well. Now these minority carriers are occurring due to temperature only. At 0 degree or absolute temperature, there won't be any minority carriers. These minority carriers are existing due to temperature difference only, means due to the it's a function of temperature. All right, so there will be holes. Holes, how holes are formed? If an electron from its space, occupied space, leaves and move to a conduction band, this electron will leave a hole. Similarly, in a p-type semiconductor where we dop with trivalent atom, there you have holes as majority carriers, but along with the holes there will be electrons as minority carriers. Same, here also the minority carriers are due to temperature, increase in temperature. Here what we are going to do is, we have a p type semiconductor and an n type semiconductor. We are combining it, sandwiching it, such that we form a p-n junction. Just let us see what are the properties and what are the phenomena associated with this p-n junction. See, even this atom will have hole, this will have electron. Okay, let us see what happens. See, once it is joined, as I already said, this hole is a strong attraction or center of attraction for electrons. These electrons will readily move towards these holes, the neighboring holes. Now, once that has happened, once it has happened, who is losing this electron? Our atom is losing the electron. Once the atom loses an electron, that atom becomes ion. Ion means it is positive, positive ion. It will be massive. Atoms are massive compared to electron, especially germanium atom with 32 electrons or 32 protons. It will be very heavy. So this positive atom will stay while this electron will start moving. So it happens in with all these three uh, atoms, and therefore ions, strong ions in the sense they are heavily massive, immobile. What are these electrons and holes are mobile, means they are small in size, they can move through the interstitial space. Okay, so but these atoms or ions are massive and having larger size, so they cannot move. Now once they have formed, there is a positive uh, charge developed on the n side, one end of the n side, and there is a negative charge which is developed on the other side. Due to this formation, now with some electrostatics, positive charge and negative charge, two equal and opposite charge separated by some distance, that is nothing less like our dipole. Okay, so there is a electric field from positive to negative, so there is a electric field developed. Now electric field will be developed in the negative direction of the change in potential, right? Electric field E is equal to minus del V. It is in the negative direction. That means electric field is in this direction. Change in the potential from lower to higher. If you didn't understand, you draw just a potential field. Electric field is in this direction, right? Potential is decreasing in the same direction. Sorry, potential is decreasing from, yeah, EV. So you can write E is equal to, yeah, E is equal to minus del V. This is a formula in the negative direction of the change in potential. Okay, that varies. Now once this has happened, there is a potential increase from where to where there is a negative potential, there is an increasing potential, so plus V. This change is V naught. That means there has developed a potential difference of V naught across these two junctions. and this junction is called depletion region where it has developed. Now this potential, for example, this electron has to come to occupy this hole. So once it moves from here, it is easy to move up to here, but once it reaches here, this positive charge will be pulling this electron towards this positive charge, while this negative charge will be against this electron coming. It will be pushing it away. Alright, that means it doesn't have enough energy to cross this barrier. So that V naught is called barrier potential. This region is called depletion region. So this barrier potential prevents further movement of electron or further combination of electron and hole, thereby reducing the current. There won't be current that stops. So there develops a potential which prevents this electron hole pair combination. Next one. So once we have created a PN junction, we have a region where there is V naught. This V naught is nothing but uh, barrier potential, or you can write VB. Okay, and this region is depletion region. Now in the given figure, you can see some of the electrons are in the P region and some of the holes are there in the N region. It automatically means that we are not talking about an ideal case at temperature equal to 0. At some temperature higher than 0 or room temperature, this will happen. That means in the P region there will be some electrons, in the N region there will be holes. This is just an notes. Here you have a barrier potential for silicon and germanium. Silicon barrier potential is around 0.7 volt. Germanium, this is important. V naught or VB also you can use. There is no problem. VB also you can use. Barrier potential. Alright. Now applying a DC voltage to a PN junction. What will happen once we start applying a DC voltage? That means external supply of energy. We are giving some energy to the poor electrons that cannot combine with the holes. In the previous case, see, when we had so many electrons here who remained in the same side due to barrier potential. Once the electron has shifted, first electron has shifted, there became a barrier between this electron and holes. So they cannot move further because of that barrier potential. Now what we are doing is we are just giving them external supply from the other end, so that they will get some energy. External friend is helping this electron to cross this barrier and reach the other end. Now in that case, see, electric field was in this direction. Now there is a potential developed from, this is a minus V2 plus V, and the difference minus V2 plus V is nothing but V naught. Okay, but what we are doing, on the positive side we are giving a negative potential, where there is a positive side, and on the negative side we are giving a reverse potential. That means actually we want this electron to cross the junction. That means we are reducing the barrier potential. See, a potential is uh, there, that means positive potential. If you bring a negative charge towards this positive potential area, its potential decreases, right? Same way, what we are doing is we are trying to reduce the barrier potential. Now by doing that, how can we do? You can uh, bias this positive region with a positive potential and the N region with a negative potential. This is called forward biasing. Now what happens in forward biasing? These electrons will start moving from one end to the other. That means N region to P region, giving rise to some current I. Now what happens in this case? These electrons will start moving, and this barrier potential, once it overcomes this barrier potential, for example, if we are using a silicon crystal, it will have 0.7 volt. That means if you can apply any voltage greater than this 0.7 across this junction in a forward biasing, then this electron can jump. That is what the actual meaning is. So once it crosses 0.7, there will be no barrier against this potential we are giving the voltage. Once it crosses, it will have free movement across this, and as and when you start increasing the potential across this in a forward biasing mode, then more and more electrons will start flowing to the other end, giving rise to current. Alright. Now let us see what happens in the reverse bias. There were electrons and there were holes. Once it is reverse bias means P region is being connected to negative terminal and N region being connected to positive terminal. These electrons, rather than trying to cross this junction, will move towards the other area. That means it is increasing the earlier V0 was the barrier potential. Then since more potential is being added to the same side, V0 will increase. V0 plus whatever external voltage we are giving, V external, it will increase. Electrons will be in the opposite direction and it will not move further. Alright. Now coming back to this forward biasing, once we have done this forward biasing and we keep increasing this external voltage, external electric field, more and more electrons will start flowing. It will increase the once the more electrons start moving with a higher velocity, once the electric field is increased, it will move with higher velocity. Once it happens, this electron will start hitting the other electron which is covalently bonded. That electron will gain energy, sufficient energy to move out of the covalent bond and reach the conduction band, and they will start conduction, and it will very fast it will reach up a point where it will reach to a very high value of current. In that case you will have a very large amount of current. Now again, coming back to reverse bias, once you apply a very large reverse bias current, what will happen? Same process will happen. Electrons, when given more potential, it will start hitting the nearby electrons which are covalently bonded. Again, what will happen? there is a rise in temperature, holes will be formed, electrons will start moving out. Again there will be a rising current.
Now here you have a PN junction. PN semiconductor is being connected to positive and negative terminal. The positive terminal or the P region is connected to positive terminal and the N region is connected to negative terminal. So this is a forward connection, forward biased connection, forward biased. Now what happens here, these electrons, the negative terminal here have the electrons. So these electrons get dumped into this N region. So you have electrons here. Alright. Now even in this N region you have free electrons. So once these electrons get dumped into this N region, these electrons move forward to near the junction, and in this junction they recombine with the holes. That means in the N region the conductivity is due to electron. Okay, now once this electron recombination with the holes occur, and this electron will travel through this P region. Now once this is happening, these holes, as I said, it will start recombining with this electron. That means in the P region the conductivity is due to holes. The conductivity means the current in the P region is by holes. Now when this electron reaches the leftmost end, that means here if the electron reaches, that the electron when it reaches this end, they move to the positive terminal, because this positive terminal will be attracting this electron which is negatively charged. So this is what happens in the forward bias. Okay.
Where you can vary this resistance, voltage across voltage and current passing through the PN junction or diode. Okay, now the varied voltage you can see here, and this is in forward characteristics. That is why we are using milliampere. Forward characteristics means majority carriers will be in electrons. Now, as we have already said, what happens for up to certain voltage, there will be no increase, because it in the forward case, up to certain voltage there won't be any increase in the much increase in the current. Small variation will be there. That small variation is due to minority charge carriers moving across the junction. Now once it crosses 0.7 and 7 for germanium, sorry, is for silicon, and for 0.3 for silicon, it will start shooting up. The energy will move on, shooting up, the current will move. Now what is this? This is the barrier voltage. Barrier voltage means the voltage required to overcome that barrier potential and will start connecting. And that particular value where it shoots up is nothing but knee voltage. Knee voltage. Now in the reverse case, you have there is no current, and even though there is very less current, that current is due to minority charge carriers. That is why here you have milliamperes. and here you have microampere. That is the reason why there is milliampere, microampere. Microampere is kept for reverse bias. Why? Because the current in the reverse bias is caused due to uh, minority charge carriers. But here on the positive side, both minority and majority carriers are responsible. But once it reaches a point, certain voltage, you cannot increase further. If you increase further, your diode is damaged, and that particular voltage where it damage is called breakdown voltage. In mm, our Zener diode, we will be using this particular breakdown voltage for doing our uh, for practical purposes more.
Understanding the two quantity once again. Breakdown voltage. Now what is breakdown voltage? This is where the breakdown voltage, and what is that? This is the minimum reverse bias. See, this is towards the left. Minimum reverse biased, reverse bias voltage, minimum reverse bias voltage at the PN junction. That means here you have PN junction, the minimum reverse bias. So this is a characteristic curve. PN junction breaks down. So minimum, let me write minimum reverse bias voltage at which PN junction breaks down. So that is called breakdown voltage. Breaks down. And once it breaks down, there will be a sudden rise in current, reverse current. Okay. Now I would like to introduce another quantity called knee voltage. Knee voltage. Now this is the forward voltage. So this is the forward voltage at which current through the junction starts to increase rapidly. So this is where it increases rapidly. Okay. So this is the minimum voltage. So that is the knee voltage. So knee voltage is where the forward current or forward, this is occurring in the forward region, and breakdown voltage is occurring in the reverse region. So here when it increases rapidly, it is called, at that point is called knee voltage, and in the reverse region, that particular breakdown or region where starts increasing in the reverse direction is called breakdown voltage. For silicon diode, your knee voltage is around 0.7, 0.7 volt, and for germanium diode, your knee voltage is around 0.3. It will be given in the question, don't worry. So this is also called barrier voltage. Barrier voltage. It is represented by either V0 or VB. Okay. So this is the minimum voltage where your diode starts conducting. Diode starts conducting. For ideal diode, we have already seen, for ideal diode, this is taken as 0. VB is equal to 0. For if you are taking approximate model or simplified model, this V0 value should be added.
Now, maximum forward current. Maximum forward current means through the diode, we cannot send as much as current we want. As earlier stated, the electrons, the collision with the electrons will lead to a damage of our current. So there is a maximum current through the diode possible. Okay, that is called maximum forward current in the forward direction. Now what is peak inverse voltage? Peak inverse voltage means the maximum reverse bias voltage that it can withstand. Mainly it is used in rectifier. You might have used our in our lab, rectification. uh, See, uh, we have a 220 volt supply, AC supply, and we are stepping it down to 4 to 4, or that means minus 4 to plus 4, or minus 6 to plus 6. We will step down to this much volt and then use our rectifier, and we get the rectified output. This is what we get. Now why do we need to step it down? Why can't we use directly 220 volt in our rectification? Because this has got a peak inverse voltage. That means even not only peak inverse voltage, even higher voltage, positive voltage also if we use is a problem. Our diode will get damaged. That is one reason. Okay, why we are stepping it down. Or what is another reason? Another reason is if we use 240 volt for rectification, uh, your college will be a history. Now, maximum power rating. Maximum power rating means power equal to V times I. We have maximum current that can flow, maximum V that can be supplied. That is P max. Maximum power. Or if it is maximum, this has to be minimum. There is a power, maximum power that diode can withstand. It need not be always maximum and maximum. One it is maximum, the other has to be minimum. Even then that P maximum as this also will be using in the case of a Zener diode. That is maximum power rating. All these characters or parameters will be described when you go to a shop and buy this diode. They will tell you what maximum power rating, peak inverse voltage. If you are using it for rectification, they will tell you about the peak inverse voltage. If you are asking for stabilization, voltage stabilization, they will ask you for what is the maximum power rating. Okay, yeah. The conductor is semiconductor is formed by covalent bond discussed earlier. A semiconductor has negative temperature coefficient, again discussed. When pure semiconductor is heated, its resistance heated, it will start conducting. When conducting starts, resistance decreases, goes down. In a depletion region of PN junction, there is shortage of is it acceptor ions? There are ions as well as donors. What is missing? Holes and electrons in the depletion region. Because once, why there is acceptor and donor ions? Because of exchange of holes and electrons. Once the holes and electrons has exchanged, there is no holes electron. They exist together. Okay, so hole in a semiconductor is defined as it's not a free electron, is incomplete part of electron pair bonds. Incomplete part, that is second. As doping to the pure semiconductor increases, bulk resistance of the semiconductor. What happens? The resistance of the semiconductor decreases. Once the doping is done, why we are using doping? To increase the conductivity. Either if it is N type or P type, it is same. PN junction acts as controlled switch. Now, what do you mean by controlled switch? When you give some condition to the switch, that is called controlled switch. If it is like this, or if it is greater than, something like that, that is controlled. Now bidirectional switch, that means in both way it is a switch. That means for positive half cycle or positive potential as well as for negative potential, it is acting as a switch. Unidirectional switch, in one direction it acts as a switch. That means only in one direction it conducts conducts only in one direction. It's true, because in the reverse bias it doesn't conduct. So that is answer. Third. Now, if the temperature of the extrinsic semiconductor is increased, the pronounced effect is on junction capacitance, minority carriers, majority carriers, none of them. We know that the minority carriers as well as majority carriers will increase. Why? Because once the temperature increases, certainly what happens, the electron, bonded electron will move on. But the question is, where is the pronounced effect? Pronounced effect means larger effect. For example, there are 10 minority carriers and 100 majority carriers. Okay, and due to heating, 10 electrons has left. So if 10 electrons has left, minority carriers will add by 10, majority carriers also will get added by 10. Where is the pronounced effect? Here is a 10% increase in the majority carriers. In the minority carriers, what is the increase? 100% increase. So there is a 100% increase in the minority carriers. So pronounced increase is on minority carriers. Now in an intrinsic semiconductor, number of free electrons, first option, equals the number of holes, because in a intrinsic semiconductor it is not asking about at absolute zero, that means zero temperature. No, at any temperature we are talking about pure semiconductor. In that case, number of holes and electrons are same. Less than hole, none of them. Okay, at absolute temperature, intrinsic semiconductor has absolute temperature means zero, no holes or free electrons. So okay, anybody with a 10 out of 10?